Hey all, welcome back. We are going to continue with polar equations now. Now we're going to move on from just polar coordinates. We have talked about plotting polar coordinates. We've talked about how polar coordinates are really represent a more natural way of describing a place's location rather than horizontal distance and vertical distance. Polar coordinates represent a location with both distance and direction. Distance being that r, that distance from the origin, and direction being our angle theta measured in standard position. We've converted back and forth between rectangular and polar coordinates, and we are going to move on to equations. We know equations represent a lot, really, depending on how you're using them. So we're going to talk about converting between rectangular and polar equations. And for those of you thinking, why? Not only are polar coordinates the more natural way of describing a place's location, for those of you moving on to calculus, polar coordinates will come back. And also, we will actually see between today and our next notes session that there are some equations that we've encountered in the XY coordinate plane that actually can be more easily represented in polar form. And like I said, we will get to that both today and the next notes session that we have. Now, I guess along with that, there are some equations that actually look terribly nasty in polar form and are better represented in the XY coordinate plane. So we will discuss that. We will actually look at what polar graphs look like with our next note session as well. If you have access to your handy dandy graphing calculator, that will absolutely help. I'm trying to get you all access on your computer at the very least, because I know some of you don't have these at home. I'm also trying to figure out how I'm going to have you plot polar graphs outside of your calculator, because if you're anything like me, you don't have a printer at home, and polar graphs take a special type of graph paper. But I guess that is for the next time we meet, and hopefully I'll have it figured out by then. But without further ado, if you are following along in the slides, we're going to finish up those Google slides that we've been working on. We're going to finish up with slides 9 through 13. And again, we're going to be converting equations. We're going to start going from rectangular equations with X and Y, to polar equations. So I'm going to use my daughter's Osmo screen, our Osmo reflector again. I'm going to flip this around, and here we go. So converting equations. Wow, I need some better light in here. Converting equations. There we go. Notes 14.5, we're continuing. Slides 9 through 13, like I said. So we've actually, the four equations that we use to convert between rectangular and polar coordinates are really going to be the keys for converting between rectangular and polar equations. So the two equations that we used, if we had polar coordinates and we wanted the rectangular coordinates, the two equations we used to help us get those rectangular coordinates were x equals r cosine theta and y equals r sine theta. I think I mentioned this in the last notes that we did. I always remember which one's cosine and which one's sine, because it goes with everything we've learned about trig, is that cosine always takes after x and sine always takes after y. So let's think about the rectangular equation y equals x squared. Now we should all recognize that this is the equation of a parabola. It's a really simple equation, Cartesian equation, y equals x squared. But what would that look like if we expressed it as a polar equation? So we are, again, all comes back to these two relationships up here. We are going to use these two relationships to substitute in for x and y, because ultimately, if we want to end with a polar equation, we don't want to see any x's and y's. We only want to see r's and thetas. So how can we get rid of y and x to ultimately leave us with r's and thetas? So starting here, well, y, I don't want to see a y, I want to see r and theta. But knowing that y is equal to r sine theta, I can make that substitution. Y is equal to r times the sine of theta. Awesome. Y gone. I have r and theta. Equals, okay, well, I don't have a substitution for x squared, but I do know that x is, using that first equation, r times cosine of theta, and that quantity is squared. And to be quite honest, technically, we've done it. We have expressed our original rectangular equation of a parabola, y equals x squared, to a polar equation. Now, this would absolutely be one that is way more easily represented in rectangular form. This looks really complicated, but we will get that into our calculator and show you, prove to you that that really still is a parabola. We'll do that later. We'll do that next time we do notes. But how do we express, is this really how we express a polar equation in most simplified form? Well, with rectangular equations, we're used to simplifying them to the form of y equals. With polar equations, we simplify them to the form of r equals. I will make that a note up here. We typically simplify them, if at all possible, to the form r equals. Now, I'll be quite honest, if you got this far right now and you're like, how do I get r by itself? We can keep practicing with that, but we're going to walk through how do I get this to r equals. We're going to walk through that together. So first thing I notice, if I want to get this to say r equals, I have parentheses here. Now this is a times in here, so I don't need to worry about FOIL. I only have to worry about FOIL when I'm squaring something if I see a plus or a minus. With a times, I just need to make sure I do r times cosine times r times cosine, or in this case, I can, if you will, distribute that exponent. So I have r times sine of theta on the left side equals r squared times cosine squared theta on the right. And again, our goal is to get this in the form of r equals. So what I'm going to do next, I can't get this to say r equals if I have an r on both sides. So I am going to, since this is all multiplication, I'm going to divide by r on both sides. Whatever I do to one side, I do to the other. These r's will cancel, leaving me with sine theta. And here, r squared over r, the r in the denominator cancel. One r in the numerator will cancel, leaving me with r times cosine squared theta. And again, our goal with polar, we want it in the form of r equals. We'll see later on, that's the only way I can type it into my calculator. Just like rectangular equations, we want y equals to put it in our calculator. Polar, we want r equals. So to get r by itself, I'm going to divide by cosine squared theta. And whatever I do to one side, I do to the other. I'm going to rearrange it so it says r equals. Technically, I could leave it as r equals sine theta over cosine squared theta, but this also makes me realize sine over cosine, that is tangent. Thinking about our identities, that is tangent. So if I wanted to rewrite this in non-fractional form, I could, except I have a cosine squared in the bottom. But thinking about what cosine squared means, cosine times cosine, extend that a little bit. Here is our sine over cosine. There is our tangent of theta using the quotient identities. We still have a cosine in the denominator. 1 over cosine using the reciprocal identities is secant theta. And we just got our equation in the form of r equals. So the rectangular equation, y equals x squared, that of a parabola, we all know. In polar form, a parabola would be expressed as r equals tangent of theta times secant of theta. Now, which one again is the easier to express form? By far, y equals x squared. But this just goes to show you that any equation in rectangular form can be expressed in polar form. Now, what about an equation that would be easier to express in polar form? Let's try converting the equation x squared minus 2x plus y squared minus 2y equals 0. Now, y is not by itself in this case. Y would be actually terrible to get by itself. Many of you will recognize this as the equation of a circle. Circles we know are really hard to graph in our calculator. If we are able to get y by itself, then we still need to remember to do, we'd eventually have to square root, we'd have to remember to put a plus or minus in front of there to see the circle. Now, if you do remember, I did show you the app in your calculator that allows you to graph a circle in this form. But if you don't have that app or you forgot that it existed, you'd want y by itself. Well, watch what happens when we convert this to polar form. So again, the key, having these equations handy all in one place next to you somewhere would be really, really great. We want to get rid of all of our X's and Y's, and we want to change that to we want to change those X's and Y's to R's and thetas. Now, you know what? While we have these right up here, we actually had two other equations that could be really handy. If you're looking at the slides, that would be fast forwarding to slide number 10. Going from rectangular to polar, really, truly, these are the only two equations you need. But using the other two equations could make your life slightly easier. When we were converting from polar to rectangular equations, or to coordinates, we also had the equations or the relationships r squared is equal to x squared plus y squared, and theta is equal to the inverse of tangent of y divided by x. Like I said, truly speaking, going from rectangular to polar, these are the only two you need, going from rectangular to polar. However, if you also use these two, could make your life a little bit easier. And here's one place that that would happen. If I look down to this equation of a circle, I see an x squared plus y squared right here. I could substitute for x, r cosine theta. I could substitute for y, r sine theta, and square both. Ultimately, you'd end up getting a cosine squared, a sine squared, and using a Pythagorean identity. I could also just fast forward right over here and say, ooh, x squared plus y squared, x squared plus y squared, that's equal to r squared. So I'm going to go ahead and make that substitution. X squared plus y squared is equal to r squared. Awesome. Well, we still have this minus 2x minus 2y. Now, neither of these are squared, which means I'm going to have to use this x equals and y equals relationship. So minus 2x is r times cosine theta, minus 2y is r times sine theta equals 0. Yikes. Now, I did say at the beginning, this equation of a circle is actually better represented or more easily represented in polar form. Right now, it doesn't look it, but this would be one of those equations that takes a little bit more ingenuity to get r by itself. If you got this far, again, I would be totally pleased. We're going to practice. We're going to continue to practice, but I'm going to go through the how the heck would I get r by itself. I'm going to go through that with you. So here goes. First thing I'm going to ask myself, okay, these parentheses, do we need them? Do we really truly need them? The answer is no. I don't have any pluses or minuses inside of these parentheses. It's only multiplication, which means I don't really need to do any distributing. So I am going to rewrite this as r squared minus 2r cosine theta minus 2r sine theta equals 0. Now, again, just like rectangular equations we express in the form of y equals, polar coordinates we like to express in the form of r equals. So now we have to figure out how the heck do I isolate r? Well, I have r's everywhere. So I could take out a GCF of r everywhere, but r squared divided by r, still going to have one. So I'm going to focus on these two terms right here. These two terms have two things in common, a negative 2 and an r. So I'm going to leave the r squared alone, but I'm going to factor out a negative 2r as a GCF out of the remaining two terms. Doing that would leave me with cosine plus, because negative 2r divided by negative 2r, two negatives make a positive, plus sine theta equals 0. Now, some of you may be thinking, oh, cosine plus sine, that's 1. No, not a Pythagorean identity. These aren't squared, so I cannot substitute that 1. Issue, I still don't have r by itself. Okay, again, I'm going to ignore that r squared right here. This negative 2r is a coefficient for the cosine plus sine. I'm going to add this entire term to the other side. Doing that gives me r squared equals 2r times cosine theta plus sine theta. Okay. Again, I want r by itself. This r is a factor. It's being multiplied by everything in the parenthesis. So I can actually divide both sides by r. R divided by r, gone. And again, that r is a factor of these two, so I don't need to worry about taking it out of either of those two terms. And r squared divided by r, one will cancel in the numerator, denominator will cancel. I am left with r equals 2 times cosine theta plus sine theta. This is our polar form of the circle that was originally represented by this equation that we started with. Now, while I realize that took a little work and a little practice, you may notice how much simpler this really is, and you'll see in a couple class periods here how much easier this actually will be to put into your calculator. So again, the key for going between a rectangular and a polar equation lies in these two relationships. And these two relationships having on the side definitely does not hurt either. So at this point, if you wanted to do some practice going from rectangular to polar, I actually want you to fast forward to slides 12 and 13. They have some practice for you. I would highly, highly encourage doing some of that practice. Once you have done practice, then I want you to go ahead and continue with the next video, which would be converting the other direction, converting from polar back to rectangular coordinates.